In 5 minutes, you will see how a single bit in a CPU can quietly bend trust across the internet and why this matters to you, not just to engineers in a data center. If you watched yesterday's Daily Signal, here it is, you know the headline. AMD Zen 5's RDSEED instruction sometimes returns 0 while claiming success. That's the CVE 2025-6262-6. Today, we are not rehashing the fixes I covered yesterday. Instead, we'll walk 5 realistic human stories that show the real pain this tiny flaw can cause. On websites you use, on money you hold, on cloud services companies rely on smart gadgets in stores, and even on personal machines in your home. Quick teaser, at around 8 minutes, I'll show you a surprising pattern that made a production team chase ghosts for days. You will see the exact moment Entropy failed and what it felt like on the other hand. That moment is the curiosity gap I want you to watch for. Here's the setup. A CPU instruction lies about randomness. The complication? Well, systems accept that lie and build secrets from it. The insight we get from each story is the same. The technical mistake becomes a human cost. And the action I'll ask from you is simple. Stay with me, judge the scenarios, and tell me what you think we should worry about the most. If you believe this is purely technical and only affects cloud giants or kernel hackers, think twice. These stories hit people. Account takeovers, drained wallets, stored data leaks, and ruined privacy. I want you to feel that impact. Drop a short comment with your opinion down below. Which scenario worries you the most? And let's start with the first one, the web and communication incident. Alright, let's start with our first real world story, what I call the Tuesday TLS incident. Picture this, you're watching your favorite streaming service, or maybe your company's web app is handling customer logins. Everything feels smooth, until a tiny glitch deep inside a Zen 5 server silently starts bending randomness. One thread in the CPU asked for random numbers. That's what the RDSEED instruction does. And instead of getting real entropy, it gets zeros. But the CPU says, all good. From that moment, every key and every session token built on that seed is just a little less random than it should be. No alarms go off. No error messages, yet in the background, the web server is creating TLS session keys, JWTs, and cookie secrets that are not as unpredictable as they look. A few hours later, a malicious actor or even an automated botnet starts seeing a strange pattern. Tokens that should take centuries to guess are now showing recognizable fragments. Within minutes, they are able to craft a handful of forged tokens and walk right through the front door of the service. Imagine the fallout. Users suddenly locked out of their accounts, someone streaming under your logging, maybe a stolen session being sold online, no patch, no exploit kit, just a CPU doing math slightly wrong. And here's the twist. This is not a 1 in a million edge case. The Zen 5 chips are already in edge servers, CDNs, even personal workstations running web services. So, if you have ever logged into a website or managed one, the ripple touches you. Yesterday, we talked about how to detect and patch this. Today, I want you to feel what the moment means. When a website's lock icon looks secure, but the randomness underneath has already failed. Question for you, if this could silently corrupt the trust behind HTTPS, how confident are you that your online sessions are truly yours? Drop your thoughts below. I'm really curious to see what you think happens next when trust at a chip level starts to crumble. Now, let's shift gears and talk about money. Because this next story is where randomness meets your wallet. Imagine it's a regular Tuesday morning in a mid-sized bank's data center. Payment gateways are humming, authentication tokens are flying back and forth, everything is automated. Then, in the middle of that flawless rhythm, a single Zen 5 CPU somewhere in the stack quietly returns zeros instead of a true random number. No alerts, no crash, just perfectly formatted fake randomness. Within minutes, the bank's authorization system starts minting OAuth codes and one-time payment tokens that look valid, but are not as unpredictable as they should be. An attacker running an automated tool notices a pattern, authorization codes that can be guessed with frightening accuracy. They don't need to hack the network, they just start guessing tokens until one lands. And when it does, that's someone's session, someone's account, someone's money. Now, picture this, the same flow on the crypto side. A mid-tier exchange uses Zen 5-based servers for signing transactions. A nightly maintenance restart reseeds its wallet generator with the same broken RDSEED output zeros that the CPU calls random. The next day, new deposit addresses go live. They look unique, but share enough mathematical structure for a skilled adversary to reverse engineer private keys. As soon as users send coins in, the attacker sweeps them out in the same block. Real losses, real money, gone. And the cruel irony? None of these companies got hacked. They trusted the hardware, and the hardware lied. If that sounds distant, think again. The same type of entropy is behind your online banking apps tokens, your mobile payments approvals, even the QR codes you scan to send crypto. When that randomness isn't random, trust collapses from the inside out. Yesterday's episode covered how to test and patch against this, but here's what I want you to reflect on. How much of your financial world depends on blind trust in the silicon we never question? Leave me your thoughts. Would you still rely on your digital wallet if you knew the random keys behind it might not be random at all? Let's now move into the cloud, the invisible backbone of everything we do online. This one's called Noisy Neighbor Night in Region 3. Picture a busy cloud region on a regular Tuesday evening. Thousands of Kubernetes nodes are spinning up and down, containers restarting, updates rolling through. Under the hood, many of these hosts are powered by shiny new AMD Zen 5 processors, fast, efficient, trusted. But one small thing is off. The CPU's RDSEED instruction, the one meant to feed randomness into secure tokens, is actually lying. It's returning zeros and still signaling success. Now, here's where it gets messy. A local tenant, maybe just another customer in that region, notices that when they run memory-intensive jobs, the hypervisor feels unstable. Without realizing it, they are reproducing the same stress condition that make RDSEED fail. And at that exact moment, other virtual machines on the same physical host are being restarted after updates. Their Kubernetes sidecar, the tiny helper that generates bootstrap tokens and mesh identities, is asking RDSEED for fresh entropy. What it gets zeros. Those bootstrap tokens are suddenly guessable. A smart attacker takes advantage of the timing, spins up new instances on the same host and starts probing the cluster's join endpoints. One of those fake tokens hits. Now they've joined the mesh as a legitimate node. From there, it's not a breach in the Hollywood sense. No ransomware, no chaos, just quiet visibility. They can read logs, metadata, even peek at secrets meant for real workloads. It's a silent storm in the cloud. No one knows until an investigation weeks later finds an extra node in the cluster that no one deployed. Think about that for a second. You could be a customer storing your data on what you believe is a perfectly isolated cloud server, but the trust, that invisible perimeter, starts with a few random bytes inside a chip. If those bytes lie, isolation is just an illusion. This is the real butterfly effect. One bit flipped inside a processor and the ripple reaches entire tenants across a data center. If you've ever wondered what shared fate means in the cloud, well, this is it. So what do you think? Would you still feel safe if your workloads shared hardware with someone who could nudge randomness at will? Drop a comment. I'd love to hear your take before we move on to the worlds of IoT devices, where this flow gets even more personal. Now, let's take this story out of the data center and into the real world, into stores, factories, and homes. This one's called Zero Touch, Zero Entropy. Picture a nationwide retailer rolling out hundreds of new smart gateways, those little boxes that connect every cash register, inventory scanner, and camera back to headquarters. They all boot up on schedule, running AMD EPYC embedded 9005 chips. Compact, powerful, built on Zen 5. First thing they do, they call home. Each one generates a bootstrap token using RDSEED, then contacts the vendor's cloud to enroll automatically, zero-touch provisioning. But here's the catch. Under heavy load, when the install team is powering them all at once, RDSEED starts returning zeros while claiming success. Those enrollment tokens, the very proof of a device's identity, become weak, and some of them are predictable. An attacker who knows the serial number pattern of these gateways, may be a former supplier or even a reseller with inside knowledge, begins guessing tokens. They don't need to hack the store. They just impersonate a few devices and the system says, "Welcome aboard." Within minutes, rogue shadow gateways joins the corporate network. They look authentic, they pass all the checks, and they start quietly mirroring traffic. Now, think about what passes through those connections. Inventory data, POS updates, maybe even loyalty card information. Again, it's not a Hollywood breach, it's subtle data drift, invisible to everyone until weeks later, when analytics start showing discrepancies that no one can explain. This is not about someone targeting one company, it's about scale. When an embedded processor lies about randomness, thousands of devices can enroll wrong at once. And once they do, you have built an army of trusted imposters right inside your own infrastructure. It's chilling because it's ordinary. No malware, no phishing, just bad math in silicon. That's the butterfly flapping its wings in a warehouse and causing a privacy storm in headquarters. If you run connected devices, routers, cameras, industrial controllers, imagine they all share the same quiet flow. Would you notice? Let me know what you think. Could a zero-touch setup like this turn into zero trust in your own environment? Now, let's bring this story home, literally. This one's called the Weekend Rebuild. It's a Saturday afternoon, you have just built a brand new PC, shiny Ryzen 9000, lightning fast, everything fast, fresh and clean. You start setting it up, generate new SSH keys, maybe spin up your password manager, back up your crypto wallet, and sync some photos to your private clouds. Life is good, but here's what's happening under the hood. While the system's importing data and running updates, it's pulling random numbers from the CPU. And because of the RDSEED flow, sometimes it's getting zeros instead. The chip says success, and your apps believe it. They use those bad numbers to create session secrets, password reset links, maybe even encryption keys. You don't see it or feel. The screen doesn't flicker, the machine doesn't crash, everything looks perfect. But a few of those random values, the ones that keep your accounts and files safe, are not random at all. Hours later, a bot scanning the internet stumbles on your self-hosted Note app or your photo gallery. It tries a few guess tokens and suddenly it's inside. Not because you clicked a link, not because you reused the password, just because the CPU underneath basically told a lie. From there, it's personal. It becomes personal. Private photos, ID scans, tax docs, all sitting on a server you trust are now exposed. Maybe the attacker doesn't even target you directly. Maybe your data just gets swept up, sold, and reused for identity fraud months later. And you would never connect it to a random number instruction buried in your processor's design. That's the scary part. How close this one hits home. We think of vulnerabilities as corporate problems, but this is one. It could happen on your desk, on your gaming rig, on your home server. And here's another question I actually have for you. I mean, would you even know if your brand new PC was building its secrets on fake randomness? Let me know in the comments, because next we'll close this story and talk about what this all really means for trust in the digital world. And that brings us to the end of today's episode. We have just walked through 5 different worlds: the web, the finance, the cloud, IoT, and our own personal devices, all shaken by one simple thing: a CPU that lied about being random. It's wild, isn't it? How something so tiny, so deep in the hardware, can quietly reshape trust everywhere, from online payments to your home PC. If you watched yesterday's episode, you already know where the fixes and detection queries live. Today was about impact, about seeing how close these ripples actually reach us. Because at the end of the day, it's not just code or silicon, it's our data, our privacy, and our confidence in the systems we rely on. If this story made you pause for a moment, hit that like button. It helps more people find the channel and stay informed. And if you haven't yet, subscribe to the Daily Signal. We break down complex cyber stories like this one into something you can truly feel and act on. Now, I would like again to hear from you. After hearing these scenarios, which one hit closest to home? Was it the idea of forged tokens on the web, or the financial ripple, or the cloud infiltration, or the thought of your own PC quietly failing you? Drop your thoughts below. I'll be reading every comment. I am Max, Point Break Security, and this is the Daily Signal. Thanks for watching, stay sharp, stay curious, and I'll see you tomorrow when we take a look at our Thursday Strategic Signal.